All right, thank you. First, I'd like to thank the organizers for giving me this opportunity to accommodate my situation and allowing me to give this talk on Zoom. So I'm going to talk about the machine learning aided quantum chemistry discovery in the solution phase, some recent work in my group, and Emory University in Atlanta, Georgia, United States. So we all know that the availability of large, high-quality chemical data set is crucial for training machine learning models to make property predictions and allow data-driven chemical discovery. Due to the limited experimental data available, many times we need to use computational data. And it's not hard to find that successful stories in different fields of chemistry can all contribute to the emergence of some computational infrastructure ecosystems or high throughput workflows that allow us to efficiently run the quantum chemistry calculations for various type of systems. So usually, regardless of the difference of in the types of systems, usually these workflows focus on taking the input that is usually simple information about the molecule, like composition or 2D structure, and convert that to 3D structures and further perform quantum chemistry calculations and get the quantum chemistry calculated properties. And in this way, we can make large data sets very effectively. So here I'm just listing a few examples in different subfields of chemistry. Like I think in the most successful stories are in organic molecules, small molecules. There are already a lot of very mature workflows that do this conversion from composition to 3D structure and calculation of properties. And I'm just listing some examples of the workflow, but there are many beyond what I list here. So, for example, with the workflow I listed here, with our combination of RDKit and some other quantum chemistry workflows, you can generate billions of molecules with their quantum chemistry calculated properties. And for other fields, we also have such tools. For example, solid state materials, A-Flow can generate some library with millions of materials. And for transition metal complex discovery, for example, most simplified can build the initial structure of the transition metal complexes, starting from their composition, and then finally do the quantum chemistry calculation and easily generate thousands of results. And but I found that one field that we have less large data sets available. That is the solvated molecules. So if we look for data sets for solvated systems, solvated molecules, those data sets are usually at most have hundreds of data points. So here I mean hundreds of different systems, solid-solvent combination. While each data record may contain a very long molecular dynamics trajectory, but the different systems, we usually go up to a few hundreds. And I think one reason for the relative small numbers of data sets available for solvated molecules is the lacking of workflows for doing this kind of high throughput calculation for explicitly solvated molecules. So but why we have less tools in that field? So then I'm going to talk about how we run quantum chemistry calculation for solvated molecules. So usually we use two types of solvent models. The explicit solvent model, where the solvent molecules are explicitly simulated and quantum mechanical or classical mechanical level of theory, whereas the solute molecule is treated quantum mechanically. So this kind of model usually can provide us relatively detailed description of the solute-solvent interaction, but it can be computationally very costly because it usually requires high degrees of configuration sampling. In contrast, the implicit solvent models that treat the solvent as some polarizable continuum is more efficient, but it only gives some very crude description of the solute-solvent interaction. So we can efficiently use it to generate a lot of a lot of property data for solvated molecules, but the accuracy is not guaranteed. So ideally, for the purpose of generating high-quality data set, we would like to have both high accuracy and efficiency. However, as we can see, neither the explicit solvent model nor the implicit solvent model can satisfy both. So, and the aim of my group is to tackle the challenges here and make it easier for us to generate high-quality data sets for solvated molecules. So in order to tackle these challenges, we need to tackle two major challenges. One is to accelerate the method, accelerate the quantum chemistry methods such that we can run the calculations for larger systems or for a system for a longer time, for example, configuration sampling of the solvation structure. The other direction is we want to streamline the workflow, especially for the explicit solvent model, because traditionally, usually to set up some simulate calculation of explicitly solvated molecules, we need to first start from the chemical formula, manually set up the 3D initial structure, manually prepare the input files for the simulation, and then analyze the results, and also manually decide based on the expertise of the researcher, decide what method we use. So if we want to do high throughput generation of the data, we want to replace this manual procedure by some data-driven automated approach, such that we can automatically generate the solvation configurations, post the processor calculated results to make them better predict the experiments, or automatically recommend computational methods instead of relying on individual researchers' expertise. So in this talk, I'm going to only focus on the right-hand side of this graph, although my group also works on developing GPU algorithms to accelerate quantum chemistry calculations. I'm not going to talk about that. So I will first start talk about, just based on this summary, I'm going to first talk about how we automate the generation of solvation configurations. So as I mentioned, it's not simple to set up explicit solvent calculations because starting from the composition, we know what's a solute and a solvent. We usually need to fit the force field for the solute and solvent molecules because for many practical applications, for example, organic synthesis, the molecules that the researchers care about are not some molecules with a standard force field, and we need to start from fitting the force field. And then we need to generate the solvent box topology files, run a sequence of molecular dynamic simulations at MM or QMMM level. And finally, we extract some micro-solvated clusters that is not too big, such that we can then use the cluster for quantum chemistry calculation to get the property or chemical reactivity we want to evaluate. So this requires a very long procedure, and requires a researcher to be familiar with multiple simulation packages, carefully choose some simulation parameters, which is non-trivial, especially for junior researchers. So there are already some solutions to this complicated procedure. So first, there are already some packages developed that avoid the complicated setup of the MD simulation, but rather directly use some global optimization or stochastic generation algorithms. So for example, Professor Ryer's group developed this stochastic generation algorithm to directly generate the solvation configurations without the traditional way of preparing the explicit solvent model. Yes, and another work is done by Dr. Zhang in PNNL. They developed this cluster global optimization algorithm. So these can help us a lot in many use cases. But in some other situations, we still need to run molecular dynamics. For example, we want to do some enhanced sampling or study some reactions. So the molecular dynamics step sometimes cannot be avoided. So then we still need some scheme to make this whole procedure automated. So that is what my group focused on. So we to make the complicated procedure work in a high throughput manner such that we can streamline the generation of explicit solvent data set. We developed this open source Python package, AutoSolvate. So the user only need to provide the XYZ coordinate of the solute and then choose what solvent they want to prepare. So in the initial version, we only offer a few options for the solvent, but for our more recent version, we allow any arbitrary solvent provided by the user as a XYZ file. Then the workflow will automatically fill the false food, generate the solvent box, the topology file, run the molecular dynamics simulations, and finally extract the micro-solvated cluster that can be directly used by quantum chemistry calculation. And now we have both a command line interface that you can do all of these steps in one line of command for automated workflow, whereas we also offer this graphical interface for junior researchers, such that they can just click into all the options in this interface and do all this automatically to provide a more user-friendly way to run this tool. And it's available for different platforms, Linux, macOS, and Windows. Everything is open source. So that was what the program was like last year. And right now we're still doing active development, and we added some new functionalities, or we are developing some new functionalities in the branches, not yet merging into the main version of this program. So I just want to mention a few. So first, now we can allow multi-component solid in multi-component solvent. So we can do simulations of complicated systems like that involves reactant and product for if we are studying chemical reactions. And then we also incorporated some umbrella sampling techniques, workflows into this, such that we can sample along certain coordinate of interest, and we are also trying to improve the software interoperability. So before our workflow only rely on the Amber, Tarkham, Gaussian, these packages, but now we're trying to improve the interoperability with other quantum chemistry packages and molecular dynamics packages. And we also added support for like machine learning force fields, such that we can also use machine learning force fields to do the solvation configuration sampling. So, for example, with the new features, now we are able to run automated simulation for many donor acceptor systems to do umbrella sampling along their separation coordinate. These simulations used to be done manually, but now we can do it efficiently for hundreds of systems. And more recently, we implemented a web interface. We call it AutoSolvate Web. So this is going to be released next year. For this web interface, we use the cloud computing technique such that the simulation, MD simulation, and quantum chemistry calculation needed will be run on the NSF cloud computing resource, such that the user does not need to have the hardware in order to run these simulations. Before, the user need to download AutoSolvate and still need to install all the required packages on their own resources. But now this tool can be used by anyone without the requirement of hardware. Okay, so I think I don't have a lot of time remaining, so I will quickly go through the second aspect. So what can we do once we have such a workflow that can allow us to generate the data? So I'm going to show one example that we try to improve the accuracy of the calculations of solvated molecules by using the data we generated through the workflow, such that we can get the results better compared with experimentally measured results. So, for example, redox potential has been widely studied in quantum chemistry community. So there are a lot of calculations about redox potentials, but many times we find that there is a significant deviation from the experimentally measured results. And one major reason is that the solvent models used in the calculation are not perfect. That can introduce significant errors. So, for example, here I'm showing I took the ROP313 data set curated by Professor Grammer's group. That is one of the biggest experimental data set available for redox potential. And it has about 300 redox couples in this data set. And by performing quantum chemistry calculations, we can see that there are significant errors compared to experimentally measured redox potential. So there are some like systematic bias. For example, for the organic molecules, all of them tends to stay below the diagonal. For the organic metallics, it's also the distribution is like biased. At the same time, there are some very large error outliers. So we need to try to fix all these issues. So traditionally, there are different approaches proposed by different groups to solve this problem. So I think one of the earliest approaches is to use linear regression. So if we have a set of data, not a very big data set, then fitting the experimental data to fitting the calculated data to experimental data can usually give us pretty good correction. And however, for larger diverse data set, like what we tested on, the data set with hundreds of different redox couples, the linear regression no longer work well. And some other practices are like use some internal reference to do error cancellation. That's also effective, but still cannot eliminate all the errors. And more recently, there are new approaches, such as a pseudo-quantum isolation scheme that discovered that there is a significant error related to highly solvated systems. And the highly solvated systems have imbalanced treatment of the solvation-free energy for the oxidized state and reduced state. So that error comes from the imbalancing of solvent solvation methods in treating differently charged systems. So then some empirical formula are proposed to fix this. Inspired by these previous methods, so we think probably we can use machine learning to do this correction, because some of the previous approaches, for example, the pseudo-quantum approach, the relationship between the error and the charge of the solid should be learned by the machine learning model. So then we propose the following model. We use very simple features focusing on the solute and solvent. We have only 9 features here because our data set is not big. So we want to have simple features. And then we also use the simple models. And we found that the correction is significant. So compared to the raw calculation result, the result is based on the accuracy on the test data set. So compared to the raw quantum chemistry calculated result, now we can reduce the error by at least 40%, regardless of the specific DFT functional we chose for the calculation. And we also found that after the machine learning correction, the performance of different DFT functionals also get similar. So that means the choice of the DFT functional is no longer that important. So which is also a problem we usually encountered in chemistry discovery, that usually the DFT method you use for calculating certain property of interest usually relies on the system. But now if we have the machine learning correction, then the functional we choose is no longer important. This reduces the uncertainty in the method you choose to generate the data. And we also verify this approach is also useful when the redox potential results are generated by explicit solvent model. So it can be used for both explicit solvent approach calculated redox potential and implicit solvent calculation generated data set. And we also verify that this approach can also be used for other properties such as absorption energy. And we also tested what kind of molecular descriptor is best for this kind of delta machine learning. But unfortunately, we found that the best descriptor highly depends on what kind of molecular property you want to predict. So unfortunately, there is not a rule of thumb about what kind of molecular descriptor you should use for different situations. So, okay, I think the time is up, so I will directly jump to the end. Here, I would like to acknowledge my group and who developed all these tools and methods. And thank you for your attention.
Thank you very much. Questions? So what about Monte Carlo sampling for the solvent?
Oh, that's a good question. So we haven't implemented that yet, but that's a very good suggestion. We will consider adding that support for Monte Carlo simulation in the future.
No more questions? Okay, let's thank the speaker once more for a nice presentation.